Worksheet number 4, question number 3. The first thing we got to do is with every other two-dimensional question is draw what we call a situational diagram. That just describes what's going on here. We have a 4-kilogram ball traveling north with a momentum of 11.2 kilograms meters per second. I'm going to call that ball number 1. We know that it has a mass of 6.0 kilograms and a momentum of 11.2 kilograms meters per second. I don't know what the velocity is. That doesn't really matter right now. We'll worry about that later on, okay? We have another ball that's going to the west. We'll call that ball number 2. It has a mass, sorry, the first one is 4 kilograms, isn't it? 4.0 kilograms. The second one is 6 kilograms, and it has a momentum of 18.0 kilograms meters per second. Now, when these two things hit each other, and they stick together, they collide and head off as one object, where do you think they're going to go? Roughly. That way? Up and to the left. Sure. If we have momentum to the left, then we have to have momentum to the left afterwards. If we have momentum upwards before, then we have to have momentum up afterwards as well. Now, typically what you do in a question like this, a two-dimensional collision, is go into x and y components. Pi equals Pf. Usually we'd say m1 v1i plus m2 v2i equals mvf because they stick together. But in this case, we can actually take a little bit of a shortcut here. Firstly, the first object has 0 momentum in the x direction. It's all in the y. Second one has negative 18 in the x direction. Now, some of you found the velocity of object number 2 by saying p is equal to m times v, dividing 18 by 6 to give you 3 meters per second. But then when you turn around and plug it back into here, you're going to get 18 anyways. So why don't we just go with the momentum? What? This is m times v. They give it to me already. Now the final momentum is what we're going to try to find, which is easy because it's going to be 18. That's the x component of the final momentum. Now we're going to do the same thing for the y component. Pi is equal to Pf. This time we're going to say the initial momentum of object number 1 is 11.2. If I didn't know what the momentum was, but I knew what the velocity was, then I can multiply m times v. But I've already got it. They've done it for me, right? They've multiplied m times v for me already. Plus 0, because the other one is only on the x-axis, equals Pf. So we're going to say, sorry, this is negative 18. This one becomes positive 11.2. Now we got to combine them. We've got 18 to the left, and we've got 11.2 up, and then we're going to combine them to find the final momentum. Not the velocity, but the final momentum here. Now, had I did mv over here and mv over here and solve for vf and vf, then I would be combining velocities. But since I found the final momentum, x and y, I'm combining momenta. When I do that, I should end up getting 21.2 kilograms meters per second. And when you find that angle, theta, it should work out to be 31.9 degrees north of west. All right? Now, once you've got that momentum, we're asked for the velocity, right? Forget about the initial momentum right now. We're asked for the velocity. How are we going to find the velocity from that momentum? P over V, right? V over M. P over M, I should say. There we go, finally. So 21.2 divided by 10 kilograms gives me 2.12 meters per second, still at an angle of 31.9 degrees north of west. Now the only issue is what's the initial momentum? Same thing. Same thing, you don't have to do anything else. Does that make sense? Don't try to say, oh look, 6 kilograms, 18 kilograms meters per second, that's 3 meters per second velocity. This is 2 point whatever meters per second velocity. Like, it's okay to do that, but don't take those two values and then try to resolve them as a 3 and a 2 point something. You can't just combine the initial velocities. You can't do that. Now, there is another shortcut though, I don't know if anybody spotted this. You do have an initial momentum of 18. You do have an initial momentum of 11.2. You can find the initial momentum using 18 and 11.2. When you do that, it works out to be 21.2. So here I found the final momentum and then said, oh, the initial is the same thing. Here I found the initial momentum and said the final is the same thing. So this, finding the initial momentum here, actually didn't require me to do the law of conservation of momentum, right? All we did was added the two initial momenta together. Is that okay? Now, keep in mind, I didn't add them up as like 3 plus 4 is equal to 5. Sorry, 3 plus 4 is equal to 7 kind of thing. I added them up as a 3 plus 4 is equal to 5 kind of thing, a vector analysis, right? 18 plus 11 is not 29. 18 plus 11 is 21. Okay, that's a pretty common mistake I see in a question like this. Actually, when a question says, "What's the total initial momentum?" People say, "Oh, it's 18 plus 11, 29." Well, it is 18 plus 11, but 18 plus 11, when we're adding vectors, works out to be 21, not 29. So do it either way you want. Go through the law of conservation of momentum, find the final, and say, oh, that's the same as the initial. Or you could actually find the initial first and say that's the same as the final. All right? I want to do one more example with you here. This is on the sheet that I handed out to you yesterday or the day before, whatever it was. So it says a 3 kilogram bundle of fireworks sitting on a table explodes into 3 pieces. The first piece has a mass of 1.2 kilograms, goes directly north at 120 meters per second. Second piece goes off at south of east. What's the velocity of the third piece? I'm going to draw my situational diagram again. Here's my explosion point, we'll call it, my X. X marks the spot where the explosion took place. Piece number 1 goes north. We'll say it has a mass of 1.20 kilograms, and it goes north with a speed or a velocity of 120 meters per second. Now, piece number 2 goes off 30 degrees south of east. Some people have trouble drawing this, right? 30 degrees south of east. We know it's down this way some way, right? South and east. But is this my angle, or is this my angle? Here's what I want you to do. Every time you see something like this, if you struggle with this at all, circle the second word. Okay? Make sense? Circle the second word. And then draw your angle from the east. Draw it down from the east. If it was east of south, then I would draw my angle from the south. Is that okay? So this one is going to go down like this. 30 degrees measured from the east. My mass is 1.1 kilograms, and my velocity is 100 meters per second. Where do we think that third piece is going to go? Where? South of west? We know it's going to go west. We know it's going to go west. We don't actually know whether it's going to go south of west or north of west. We know it's going west because there's a momentum to the east, but we already have a momentum up and a momentum down. So depending upon which one is bigger, which y component is bigger, it's going to determine whether this goes up or down. But listen, that purple one that I drew, that's just to help us visualize what's going on anyways. If I draw that one wrong, it's not the end of the world. The other ones are important. This one not quite as much so. Okay, so that's object number 3 over here. Do we know what the mass of object number 3 is? Quinn, what is it? Mass the first plus mass the second? Not quite. Spencer? Subtract that from the total mass of 3 kilograms. Yeah. So we're going to say 0.70 kilograms. Now, if you were in my class last year, you know exactly where I'm going next. If you weren't in my class last year, you probably still know. Okay, there's a phrase that I like to use. I used it a lot last year. I used it a couple times this year already. What is it? I don't like funny angles. I got this 30-degree funny angle. If it's 0, 90, 180, those aren't funny angles. Those are fine. I can deal with those. 30 degrees, I don't like that. So I take it off to the side here. I draw it as a triangle here. And I get rid of the funny angle. Actually, let's make this another color. There's my 30 degrees. There's my x. There's my y. And there's my 100 meters per second. Now, if I want to find the x component of this, we're going to say cosine 30 degrees is equal to x over 100. X is equal to 86.6. Okay, we're going to do almost the same thing for the y component. Sine 30 degrees is equal to y over 100, or y is equal to 50 meters per second. Now, I usually like to box that off just to show me that it's kind of aside from the main part of the problem. And now, what I sometimes even do is replace this. Object number 2. I told you I don't like funny angles, so I completely get rid of it. I draw this one at 86.6 meters per second, and I draw this one at 50 meters per second. So I've just turned object number 2 into 2 separate vectors, an x and a y, which makes it a little bit easier to deal with when I go to do my x and y components. So let's do that now. We'll say pi equals pf. The initial momentum is equal to 0. The final momentum is 0, because object number 1 is only y component, plus 1, what is it? 1.1 kilograms. Times 86.6. Okay, let me do that in green, actually. Color code it a little bit better here. Plus 0.70 times V3F. See what we've done there? It's not 1.1 times 100. It's 1.1 times the x component of 100. And I just found the x component a minute ago when I get rid of that silly angle that I don't like. Let's figure out what that is. 1.1 times 86.6 divided by 70 gives me 1.3609 negative. And then we do the y components. We're saying pi is equal to pf. For the y component, 0 initial momentum equals 1.2 times 120, because that's all y component, plus 1.1 times what? Yeah, cool. Yeah, I think I did, didn't I? What did I do? Oh, no, you're right. Yeah, so it's going to be, is it 13? 1.1 times 86.6 divided by 0.7, 136. Yeah, sorry. Thank you. That's going to be negative 136.0857 meters per second. Okay, so what is the y component of that 100 meters per second that we got rid of because they didn't like funny angles? Kessler? Negative 50. Plus 0.70 again times V3F. We'll solve for V3F here. 1.2 times 120 plus 1.1 times negative 50. Take it to the other side by subtracting negative 89 divided by 0.7 gives me 127.143. And it is a negative value. Well, now comes the easy part, right? This is definitely the physics 20 part now, where we say we got one that's 136.0857, and we got 127.143. And we can find that resultant by doing the Pythagorean theorem in the inverse tan function. So really, how is this different? How is this different from what we've seen? That's it. That's it. The 86.6 wasn't given to us. We had to find it. The 50 wasn't given to us. We had to find it. We were given a funny angle, and we had to find the x and the y from that funny angle by doing this stuff up here. Guess what? Yeah, no, you do. If you're finding the final velocity, you do need to find theta, because velocity is a vector, right? So you're going to find v by using the Pythagorean theorem. You're going to find theta by doing the inverse tan function of opposite over adjacent, 127 over 136. Perfect. 6 minutes left. Let's take a look at the next three questions, 4, 5, and 6.